Hello, my name is Yankova and I'm a postdoctoral researcher at the University of Manchester. My talk today will cover an improved local approach to cleavage fracture that attempts to capture both the temperature and the constraint effects in the ductile to brittle transition regime in RPV steels. To start with, let's look at the macroscopic view of cleavage fracture ferritic steels in the ductile to brittle transition regime. When measuring the fracture toughness, a large scatter is observed at a given temperature, which suggests that there is a stochastic process controlled by the microstructure. Also, we find that the crack tip constraint conditions lead to a change in fracture toughness in the material. Two different approaches for predicting cleavage fracture exist. The traditional global approaches, which rely on a macroscopic measurement of a cleavage fraction toughness parameter, and their main advantage of these methods is that they're simple to apply. However, the global approaches also have a number of limitations, including their limited ability to predict the effect of constraint, their inability to predict temperature, and also there is a need for high conservatism when using these approaches, since they cannot predict scatter effects. As an alternative, the local approaches were developed in the 1980s. These are probabilistic methods that couple the local fracture stress with mechanical analysis. Their main advantage stems from modeling the correct physics on a microstructural level and therefore capturing the stochastic nature of cleavage. However, the challenges are related with the modeling of the correct physics on a microstructural level using a simplified model for a very complex interaction of microstructural effects and using a limited knowledge of all physical mechanisms. And additionally, we also need to keep these models simple enough for engineering purposes. Considering now the microscopic view of the cleavage mechanism, we start with some randomly distributed second phase particles in the material. A microcrack initiates the particle assisted by plastic deformation of the surrounding matrix. The crack propagates firstly across particle matrix interface and then across the matrix until it is arrested at the grain boundary. Not all particles will break. In this schematic, we see the three alternative routes for a second phase particle. It may decohere and form a void. It may break and then blunten again, form a void, or it can break, propagate through the matrix and form a sharp microcrack. Out of all sharp microcracks, those with a size larger than the critical size determined by Griffith's criterion will become cleavage initiators. In the statistical model, the cleavage fracture is modeled as an inhomogeneous spatial Poisson process with points corresponding to cleavage initiators. Three assumptions define this type of process. We have independent failures of non-overlapping volumes. We have a probability of failure for a unit volume proportional to its volume. And thirdly, probability of more than one failure in the unit volume assumed to be zero. From there, we can calculate the probability of failure of a volume element and the probability of failure of the whole solid. Next, we represent the tail of the particle size distribution with a power law. So the particle size distribution is something we can measure in our material, but the size distribution of microcracks and cleavage initiators we cannot measure. And so we assume that they have the same scales and shapes, but different size densities, as shown in the slide. Here, we need to introduce a thinning function of the Poisson point process, which will represent the fraction of particles converted into microcracks which are eligible for cleavage. Okay, so this thinning function will allow us to say if a particle can or cannot actually form a microcrack, and it will change with temperature. Next, putting it all together through this schematic, we can express the total probability of failure of the solid, here in the bottom left. Using Weibull statistics, the crack driving force is expressed as the Weibull stress, which has a shape parameter m, and additionally we have a scaling stress sigma u. So this was the base of the original local approach to cleavage developed by Bermin in 1983. Previous approaches in literature considered usually an empirical fit for our shape parameter m, but doing empirical fitting loses the physical basis of the model, and so we need to find a better alternative. Let's consider how does the Weibull stress vary with the shape parameter m in the ductile to brittle transition regime. We see firstly that for 4 temperatures that we were considering, the curves, the Weibull stress curves don't intersect within the considered range of the shape parameter m, and therefore calibration for the shape parameter would not be feasible for the temperature dependence. Next, we found that scaling with the plastic zone size led to coincidence of the Weibull stress curves. So we can conclude that there are equal numbers of cleavage initiators for a given percentile toughness for each temperature, but spread in a larger volume. And so the volume density of cleavage initiators would decrease with increasing temperature. Also, in some of our previous studies, we found that the change in the material deformation properties with change in temperature was insufficient to capture this change in fracture toughness across temperatures. And that led to the conclusion that there was a need for additional material properties, parameters that would capture this fracture toughness scatter. The idea of applying a thinning function to the pulse and point process is not new. And in fact, the original Bermin model uses the Heaviside step function of the plastic strain. Also, in our previous work, we extended another form of correction by an empirical fit to the Weibull stress dependence using an exponential dependence of a material parameter. However, there was still need to base the thinning function on the physical processes of cleavage. And so this is our latest proposal of a thinning function, which is based on a normalized free energy f of k, which is a function of temperature and shear stress. So this is based on a recent model that represents the dislocation obstacle interaction in BCC metals, where the plasticity is controlled by the formation of kinks and the intrinsic temperature-dependent lattice resistance. In this model, the researchers found that based on a characteristic length scale, L star, and how it compares to the distance between kinks, D brackets, there are 3 modes of operation. So we have ductile failure, we can have a ductile plus brittle mode, and we can have a purely brittle mode. And through basing the thinning function on this f of k free energy of kink formation, we can see that based on where we are locally in our FE model and what's the value of the shear stress, we would be operating in a different mode. So here we see that when plotting the thinning function as a function of temperature and stress, we observe the expected behavior. At low temperature and stress, the thinning function is close to 1, which means close to all particles might form cleavage initiators. And as temperature increases and stress increases, the fraction of particles forming sharp microcracks decreases. And so this finding might provide explanation for both constraint and temperature effects on the thinning function. Okay, so next, moving on to some results. These are the material properties that we used. The model material is the Euro material A, a reactor pressure vessel steel. You can see the fracture toughness data that we have for 1T compact tension specimen and a Sharpie size sharpie-sized single-edged notch bend specimens. In the case of the single-edged notch bend specimens, we have two different types of constraint with deep and shallow cracks. And we also have the particle size distribution for this material. So these are the finite element models used and the details. Quarter specimens in Abacus are modeled using different finite radii proportional to the CTOD at the characteristic J node for the corresponding temperature. Okay, let's look at how the Weibull stress using the S-constructed thinning function looks. We see a very good coincidence of the Weibull curves for both types of specimens at the experimentally measured J node. For instance, the CT curves fall within 5 to 12% if we take the minus 91 degrees Celsius temperature as reference, and for a large part, they fall within 2%. We see a very good coincidence additionally between high and low constraint of the SANB specimens for the minus 110 degrees between the purple and the yellow line. So all values are within the uncertainty of 12%, which we found in sensitivity study of the uncertainty in the mechanical properties. So how do we use these curves? Let's say we choose m value equals to 10. Next, we need to choose a reference temperature, for which we find that after experimental measurements, the characteristic J value is 57.6. From there, we use the FE model to calculate the Weibull stress at the J node value. And since the Weibull stress must be equal at a given J percentile, we can then predict the J node values at the other two temperatures. So the advantage of this prediction method, we only require fracture toughness test at a single temperature and the deformation properties at any other temperature. Next, we see that in our dataset, we also have the experimentally measured fracture toughness at the other temperatures. And so we can compare how much the results vary depending on the chosen temperature basis for prediction. Here you can see results for two different shape parameters M, and all predicted J values were very good. We found that the accuracy of prediction varies with the M value. And also, since the Weibull stress curves are quite flat, sometimes a small difference in the Weibull stress resulted in a significant difference in predicted fracture toughness. So this is something we'll address in future work. Considering the SANB specimens, there were similar accurate results, and the model was able to capture the increase of fracture toughness with the loss of constraint of this much smaller geometry compared to the compact tension specimen, and also the loss of constraint at minus 110 degrees for the shallow crack. Next, we can see that the prediction curve, so the fracture toughness is a function of the normalized temperature with respect to T naught. Comparison is made between the master curve and the proposed model. The model was able to capture the scatter in the data and the trend better than the master curve. We also need to compare how the model behaves against other models in the literature, which would be done in future work. And so in summary, the local approaches to fracture methods have the advantage of modeling the physical processes governing cleavage, but some improvements are needed. The mechanical fields obtained using FEA were found to be insufficient to capture the change in fracture toughness across temperatures. Our theoretically based thinning function has the expected physical behavior of decreasing with increasing temperature and with decreasing shear stress. The advantage of the prediction method is that the only required measurements would be the fracture toughness test at a single temperature and the deformation properties at any other temperature that we would like to predict fracture toughness. The calculated Weibull stresses for a range of temperatures and constraints were within 5 to 12% of each other across all Weibull shape parameters M, with the majority falling between plus or minus 2%. It captured the change of J naught with temperature and predicted J naught across different constraints at the same temperature without any cross-calibration or modification. And finally, the model works for two very different types of geometries, standard 1T compact tension and shabby size single-edge notch bend specimens. Okay, thank you very much for your attention. Thank you to the sponsors for funding this project, and I look forward to answering any questions that you might have. Thank you.